jump into this. There are two main things we're going to do today. We're continuing with taking a function and finding intervals where it increases and decreases, and finding the y-coordinates, right? Finding the maximum and minimum value of that function. So this is my first one. I'm going to try and do as many of these as you can. I think the best practice is essentially, the best way to learn is plenty of practice. So finding the derivative is basically just a power rule. I'm not trying 3 times 28, not today. Oh, I was right. I thought it was going to be that. Okay, there's your derivative. If it's a polynomial, you don't need to look for undefined. What you do need to look for is when it is 0. Anybody tell me a good common factor to pull out here?
(28x squared).
And that'll leave me with an x, take away 3, I hope. Agreed? Right. So what does that give me? It gives me what we call critical numbers. It gives me 2 x coordinates where something interesting is typically going to happen. And once you've got them, you draw this little number line guy, and you make sure that 0 and a little bit extra. You go 1, 2, 3, and a little bit extra. And you set up what's called a table of signs, which is more like a line of signs. So x equals 0, the derivative is 0, and x equals 3, the derivative is 0. I'll do my working over here. And then you find what are called test points. These are values of x where you're going to find out what the derivative is equal to. And you don't need these extra dotted lines, but for me anyway, seem to help. Would you agree you've got region 1, region 2, region 3, right? The whole thing is broken into 3 regions. So I'm going to choose as my test point -1. What about this region? What's your test point going to be?
1.
Yeah, why not? Could have used 2, yeah. Could have used 1.733, yep. Anything will work. And over here I'm picking 4. Try and pick numbers that are nice, things you can do easily. Then we find the value of the derivative at these test points. And we don't care what their number is. I don't care if it's 42 or 57. I just care is it plus or minus. So I am going to plug in -1 in here, 1 in here, and finally 4 in here and get the answer. Now I could just simply do it in the calculator as a table of values, but let me show you another way that some people like to use. Let's do the derivative of -1. 28 -1 squared is positive. Would you agree? And -1 take away 3 is negative. So won't those two give me a negative answer? And since it's only the plus or minus that I'm interested in, that's all I need to do. I don't care if it's -50 or 5. I just care it's minus. Do the next one. You want to do f of 1. Isn't 28 times 1 squared positive? Isn't 1 take away 3 negative? Isn't that combination, when you multiply them, also negative? And last but not least, x equals 4. Right, so you want to find a value at 4. 28 times 4 squared is positive. 4 take away 3 is also positive. And so this combination is positive. Did you like that shortcut? Right. Don't like the shortcut, just do it in the calculator, right? Whatever one suits you best. So now that we've got all those answers, I'm going to put a negative here, a negative all the way here, and a positive here. Now you want to answer, when is it increasing? Right, the original function is going to be increasing when the derivative is positive, so that's 3 to infinity. When's it going to be decreasing? Right, I think me and WebAssign disagree here, but I'm sticking to my guns because I'm right and they're wrong. See how this is negative, then 0, and then negative. It's decreasing, and then it's decreasing. But at x equals 0, it isn't actually decreasing. The derivative is 0, right? It's not negative. So it should, and I hope -1, the question I saw, didn't do this, but I hope it would. That's what your interval should be. Do you see how you just miss out the 0? Now, we also want to know local max and min and where they are. And I'm bringing this guy a little bit closer to me. A negative derivative means the function is coming down the hill, right? Sloping down the way. A 0 derivative means that it's flat. And a negative derivative means it's coming down the way. That guy is not a local max or a local min, right? I mean, it does have a name. If you want to know it, it's called a horizontal point of inflection. But that doesn't really matter because we're only interested in max and mins. Now, what about at x equals 3? Well, it's negative here, 0, and then positive. Ah, can you see that I have a minimum at that point? So the question is find any max and mins. So you would be able to say there's a minimum. And for a maximum, you just put in the word none. And for the minimum, you don't put 3 in. I believe they want to know the value of the minimum. So what you do is you find out what the function is equal to at x equals 3. So that means the value of that. So 7 times 3 to the power of 4, take away 28, 3 cubed plus 2. And 7 times 3 to the power of 4, take away 28 times 3 to the power of 3, add 2, and the answer I get is -187. So that's the only thing you put in. Are we good with that?
Isn't there another minimum?
I
Well,
hope not.
because like it goes down at 0 and then it comes back up. So wouldn't there have to be another minimum or no?
Where do you think that's happening? I can't see where you're thinking.
Maybe at like x equals 2, because it goes down after 0 and then it has to come back up and then go back down.
No,
I don't know.
No. So all of this is negative. So it's continuously coming down. Right. Right. So it's going to go, this is a very rough guide of what this will look like. If you pick this up and match it to that, the function's going to look like this. Right. That's at x equals 0. And that guy there is at x equals 3.
Oh, okay. Okay.
Okay. So, but it's a good point. So let me show you what you could do if you wanted to just kind of verify what's going on. You could type in the original function. So I'm going to call it y equals 7x to the 4. Take away, shoot, get that thing out of the way. Take away 28x cubed. And then finally add a 2. And sometimes, yeah, sometimes, you know, you have to adjust the x values yourself. Looks like most of the important stuff is happening from -1 to 4. Right. And now I'm going to have to shrink or stretch the y values. I know the lowest answer is probably something ridiculous, like -200. Yeah, okay. It's hard to see both features at once, but can you see the horizontal thingy, then the dip and the up? And can you see that guy there should be at negative 187? Yep, and it is. Have you noticed that everything I've said has appeared on that graph? Yeah, I did everything using calculus. So we got our first guy. Now, there are lots of examples, different types of algebra that we need to deal with. So that one was kind of how you deal with polynomials, right? That's the kind of math that you would get in that case. This one is, what kind of math do you end up with when there's fractional powers involved, right? Like square roots, x to the 2/3. You do the same process. You differentiate it. You find the critical numbers. You do one of these, and then you build the shape from that. This question needs a product rule. So it's going to be f dash j plus f of j dashed. If you differentiate this guy, you get 2/3 x reduced to the power by 1. Leave the second guy alone. Leave the first one alone and differentiate that guy. And you get that. And if you multiply this through, this guy times this guy gets you 2/3 x to the 2/3 minus 14/3 x to the negative 1/3 plus an x to the 2/3. Are you okay with that? Right. Now, these two are the same, so you end up with 5/3 x to the 2/3. Take away 14/3 x to the 1/3. And I want to make it look pretty. I'm going to make my life, take it really slowly. If I just pull out the 1/3, it kind of makes it a little bit cleaner. Now, we've done this a few times, but it's always weird. Isn't x a common factor here? And it's either x to the 1/3 is my common factor, or it's x to the 2/3 is my common factor, right? 1/3, negative 1/3, I should say, and 2/3. Which power of x is my common factor?
Negative 1/3.
Seen that weird stuff, right? This is where style points comes into its own, which is kind of why I've been pushing it for so long. You pull out that guy, you get negative 14. Then you have to do this 2/3 take away negative 1/3, right? 2/3 subtract negative 1/3. What do you get when you do that?
1.
1, which I'm writing as x. Now, if I then take this guy and make the negative power a positive, and I'm going to write that again.
5x, right?
Yes, okay. There, looks a little bit prettier. That is my derivative, as nice as it's going to be. And I've left it as a third because that said 2/3, right? Now, there are critical numbers next, right? And there are two kinds of critical numbers. There's the ones that make this derivative 0. And there's the ones that make it undefined. If you want this thing to be 0, then you need to solve when is the top 0, which is x is 4/5.
I think that 4 is supposed to be at 14, right?
14. Oh, thank you. Well, that was well caught. too busy worrying about making this right, but not paying attention to the top right. So there is a critical number. Now, undefined is basically when the bottom is 0. And although that looks weird, it's not hard to solve. And we should check that these are usable, because sometimes when you have fractions, isn't the bottom not usable, so you forget it. But in this case, you can actually get 0 to the 2/3, 0 minus 7, the answer is 0, right? It works. So I'll draw my number line. I'll put in 0, and of course -1. What's that? That's 2 and a bit. So 1, 2, 3 should be enough. 2 and a bit is about here. Oops, I should put down the word undefined. And here, it's 0. So I need some test points. Okay, I got a region here, I got a region here, between here and here, and I've got a third one over here. I need some test points. In fact, I need 3. Anybody want to throw one at me?
-1, 1 and 3.
Right, make it easy, right? Make it simple. Now you're going to find the derivative at each one of those points. And I'm going to do it the quick way. That's negative, so the whole thing is positive. That's negative, that's positive, so that makes this negative. That's positive, this positive, that makes that positive. Right, so you're wondering how come I'm doing it that quick. I'm just putting in the number and saying, is the answer positive or negative? Is the bottom positive or negative? Right, I don't need to worry about what value, just that it's positive or it's negative. So, or you can do it, you know, the long way. I don't mind, we are good. So the function is going to be increasing in this area. It's going to be increasing in this area. And because the derivative is negative, it's going to be decreasing in that area. So you should be able to just write down it's increasing for anything less than 0 and anything bigger than 14/5. And you'll be able to say it's decreasing from anything between 0 and 14/5. A little bit fast, but you can fill in the details yourself. You got the gist of that? Positive derivatives means the thing's increasing. Negative derivatives means it's decreasing. Right. Now let's go hunting for local max and local mins. This one here is positive, 0, and negative. And this one is negative and positive, and it's undefined. So it'll probably, and it will be when you sketch it, it'll be one of those little corner things, you know, the ones I call cusps. And that's a minimum, isn't it? Doesn't need to be nice, right? And that's a maximum. So you would be able to say there's a maximum value and it's going to be equal to whatever f of 0 is, and there's going to be a minimum value, which is going to be whatever the value of the function at 14/5 is. Oh yeah, I have no idea what that is. Well, I know what this one is. This one's 0. And I don't know what that is, except I know it's negative. So I'll make up a number, it's -42. But can't you plug into your calculator and eventually get some ridiculous answer? And that would be it. And that's how you deal with fractional powers. Let's look at how you deal with the next situation. How do you deal with rational functions? All right, in this function here, would you agree the function is undefined at x equals 3? You agree they're a vertical asymptote, x equals 3. So x equals 3, not usable in any of my answers. Already figured that out before I do anything. What method will you use to differentiate this rational function? What rule do we use? What method do we use?
The Recursion rule?
Okay, correct. So it's going to be f dash g, take away f of g dashed, g squared. So it is going to be derivative of this guy is 2x, leave that guy untouched, take away, leave the top untouched, and differentiate the bottom. All over the bottom squared. If you distribute this, you get 2x squared, take away 6x, take away an x squared, take away is an add, all over x minus 3 squared. I have an x squared, I have a negative 6x, and I have a plus 8. It's even more important than normal to make sure you do style points on this. Does it look like the original? Yes. Have I factored the heck out of it? No. Can anybody see how to factor that quadratic?
A -4 and a -2.
Okay. So we've got our derivative. There are going to be three candidates for critical numbers. If you want to know when the derivative is 0, you only need to solve when is the top 0. And that gives us 2 of our answers, x equals 2 and x equals 4. Technically speaking, you should always, if it seems worthwhile, look for when the derivative is undefined. And the derivative is undefined when the bottom of a fraction equals 0, which is x equals 3. But that is not going to be used as a critical number. Why is x equals 3 not necessarily a critical number here? What's the problem?
Because it's undefined in the original function.
Right. Now, after saying that, I'm going to kind of break the rule a little bit, but sometimes you have to do that because of consequences. So I'll draw my guy. And I definitely want to put in a 0 here. 1, 2, 3, 4, 5. That's plenty of room. The x equals 2, I have a 0. At x equals 4, I have a 0. And at x equals 3, even although I cannot use it, I'm going to put it in as an undefined value. Because undefined values can affect when a function is increasing and decreasing. If they're a vertical asymptote, couldn't the function be like a volcano? Right? Couldn't the function be like a hole in the ground? Couldn't it also be one of each? So can't a function change from being increasing to decreasing because of that guy? So he's there not because he's a critical number, right? A place where a maximum or minimum will live, right? Because there's not going to be a max or min here, but it is there because it can change increasing and decreasing on a function, right? So if that sounds like I'm saying, don't use me, and then I'm using me, I guess I am, right? But I'm using you not as a critical number, I'm using you as a place where things can change. So I need some test points. I'll put in my little invisible lines, including this one. And I think this is the first time where we had to do some awkward choices. This one isn't awkward, and this one isn't awkward. But I have to pick somebody in this range and this one. And that is awkward because I don't have a nice number. When I don't have nice numbers, I just say, ah, to heck, pick the middle. So do you see my other two test points are 2.5 and 3.5. Now I'm going to find the value of the derivative at each one of those places. And you can find the value of the derivative with your calculator, with a table of values, or any other way that you see fit. I'm just going to do the shortcut. You plug in 1, that's negative, that's positive, so the answer is positive. You plug in 2.5, positive, negative, positive. You plug in 3.5, positive, negative, positive. And you plug in 5, positive, positive, positive. So I got what I needed. And you can. So I want to know when it's increasing. Here it's decreasing. Here it's decreasing a little bit more. And here it's increasing. So the intervals when the function is increasing. Any value of x up to 2. And then any value of x from 4 onwards. And it's decreasing when the derivative is negative. 2 to 4 might look right. But that's not what you should write down. Can you see how I've written 2 to 4? Why have I written that and not just 2 to 4?
Because it's neither increasing nor decreasing at the undefined spot.
Yes. It isn't even theoretically, isn't it not even there, right? It's a hole, right? Now, there might and there might not be local max and mins. You have to be a little bit careful when there's an undefined. So let's look at 2. Positive, 0, negative. Would you agree that's a local max then? So at x equals 2, we know there's a local maximum. And what's the local maximum value going to be? It's going to be the value of the function at 2. So 2 times 2 is 4. That's minus 4 on the top. And minus 1 on the bottom, so it's a 4. Now I'm going over to the 4 one. On this side, it's negative, so it's sloping down the way. Then it's 0, so it's flat. And then it's positive. Well, that looks to me like a local min. So I know that at x equals 4, there's a local minimum value. And the value of the function at 4 is 16 take away 8 is 8. And 4 take away 3 is 1. So in this case, it's 8. And that's the answers that WebAssign wants. Now let's go to what is or isn't happening at 3. Is there a local max or a local min happening at 3? Or just nothing? What's happening at 3?
There, I would say there's no local min or maxes, but there might be something interesting happening there still.
Yeah, it's a vertical asymptote. You're right, it's something quite interesting, but not a max or a min, right? In fact, here's the thing. If this guy is undefined, right, and it's caused by a vertical asymptote, which you can tell from your 141 world, that does not count as a local max and min. Now, can it be undefined with square roots? Yeah. Do you know the ones that are cusps? Like the previous question. That's okay. That's a local min, right? But a vertical asymptote that's pointing down the way, which may look very similar when you look at the pluses and minuses, right? That does not count as anything. So if you're looking at a rational function and you know there's a vertical asymptote, undefined, boom. That's there just to tell me whether it's increasing or decreasing, right? It doesn't generate any useful max or mins. How are we doing, guys? I know I'm going through a lot of them. At least isn't there a lot of similarity, right? You're doing the same kind of things with different types of functions. Haven't done a trig one, so that's it. Right, we've done a polynomial, we've done a radical, right, an x to 2/3. We've done a rational, right, the fraction one. Now we're doing a trig. That's kind of the whole family. If you differentiate 7 sine, you get 7 cosines. And if you differentiate 7 cosines, you get -7 sines. This one's a little bit different because we're only interested in x's in the range 0 to 2 pi. Okay, so we're not too worried about any other values. I need to find when this thing is equal to 0. Because I'm pretty sure it's not ever going to be undefined. So we are trying to solve when is this guy equal to 0. And my trig class, I think, did this on Tuesday. So this is definitely going to get the cobwebs out your brain. I need a bit more room, so I'm writing over here. Anybody got an idea how to solve this trig equation?
Well, it's equals 0 at pi/4, right?
Oh, you just happen to know that at pi/4 it's equal to 0, and you are correct.
Well, yeah, because cosine sine both equal each other at pi/4.
So you're basically you're saying I can solve this because I can tell one of the answers. But there might be a second one, isn't there? Or there might be. I'm not saying there is, but there might be. So we need a method to make sure we find them all, don't we? So what you said is correct, but I still need a method to find them all. As long as you do it to both sides is okay rule. That's basically a rule that I use in every equation I'm ever solving. What could you do to both sides to this equation?
Add a 7 sine.
Okay, let's try that. Yeah, it's a good start. What are you going to do to both sides now?
Divide by 7.
7.
Okay. Again, nothing wrong with that. You're on the right track. What do we do now? It's this last step that's the sneaky one.
Divide by cosine.
Yes. Now you might say, what good does that do? Well, isn't a cosine divided by itself 1? And what does that get you?
Tangent of x.
Yeah. Do you see that we're now on the place where we can find the answers? And yes, you are right. X equals pi/4 is one of those answers. Does anybody know the other place? Because there's a second answer where the tangent is also equal to 1. If you had your unit circle, you could do the y coordinate divided by the x, but we are kind of rushed for time, so I'm not going to wait long. If you know it, go for it. What's the answer?
I can't remember the value for it if I know where it is. It's like
It's in the
3/4
third.
the way through the
You're right.
the
That'll do. If you had your unit circle handy, you'd find out when x was 5/4, you've got it. So here is our critical numbers. And I don't need to find out when it's undefined, because that's never going to be undefined, right? It's just sines and cosines. There's no holes to worry about. So I'm going to do my guy, and he's going to start at 0, and he's going to finish at 2 pi. And since these things are quarter pies, how about 1/4 pi? I know that's a half. 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi, okay, 6/4 pi, 7/4 pi, 8/4 pi, right? Just haven't bothered to write those ones out. So we have a derivative of 0 here, and we have another derivative 0 here. And just like every other situation, we need some test points. Here's my little invisible dotted lines. So I basically got a region A, a region B, and a third region C. Each one of them is going to have a test point. Okay, start chucking test points at me. Not a lot of choice here. What would we use in A?
0.
What about in region B?
Pi.
Yeah, 4/4, I'd use pi, which is that one. And over here, how about 2 pi? Why? Because I think finding sines and cosines at those values are quite easy to do, right? I could have chosen 3/4 pi and some other stuff, right? But those ones will work well. So the derivative at 0, the derivative at pi, and the derivative at 2 pi. And I'm not going to write down 3 or 0 or 52. Hopefully I won't need to worry about that. At 0, the answer is positive. When you use pi, it's negative. When you use 2 pi, it's back to being positive. So this is negative, this region is positive, and this region is negative. So we can now answer the when are you negative, when are you positive. So you're decreasing in that range, you're increasing in that range,
I thought
and
you
you're
said the
decreasing.
first range was increasing. Was positive.
It is. I'm no good when I rush. I'm not good when I'm slow, but I'm worse when I rush. There we go. It's in front of me, isn't it? I should have seen that. Increasing, decreasing, increasing. So we are going to be doing, it's increasing from 0 to 1/4 pi, and from 5/4 pi to 2 pi. And I'm going to do square brackets only at the 0 and the 2 pi side. And it might be that WebAssign uses the convention that everybody is curved. That is, in my opinion, that is correct, but you may have to do curved to keep WebAssign happy. And decreasing, everybody's going to agree on this one. It's going to be curved, meaning you cannot use the endpoints. And these you definitely can't use because they're 0. And shapes then. Positive, 0, and negative. Positive, you're sloping up. 0, you're horizontal. And negative, you're sloping down. And here, negative, you're sloping down. Horizontal, positive. So we have a local maximum at x equals 1/4 pi, and a local minimum at x equals 5/4 pi. And the value of it will be whatever the value of the function is at 1/4 pi and whatever the value of the function is at 5/4 pi. And if you do that guy, you get 7 root 2 over 2's. You get 14 root 2, so that would be 7 root 2, and that will be a 0. How are we doing, guys? This has been a lot of stuff, one after the other, right? Okay. So I'm going to, oops, excuse me. I was going to, but we certainly don't have time. We're going to do concave up and concave down. All I'm going to do is remove those questions from the homework and the test, and we'll do them on Tuesday, because Monday is a holiday. And essentially all we're going to be doing to start Tuesday off with is a concave, to remind you how it works. You know, if you have curves like this, and suppose this guy here is 3, this guy is an x of 5, this guy over here is 7. Let's see, this is the end, this is 10. Shape is concave up when it makes a happy face like this guy does. So this shape is concave up. And it is concave down when it makes a sad face. And there is some point in this, roughly this area here. Let's say it's there. And I normally would pick halfway, which in this case would be 6, where there's a transition between a concave up meeting a concave down. So if this was your graph, you would be able to say it's concave down from 6 to 10, right? So for values of x from 6 to 10, it's concave down. And here, you would say it was concave up. And that would be an interval from 3 to 6. And this little guy here has a fancy name. It's called a point of inflection. And you will typically be asked to find the coordinates of the point of inflection. So can we pretend that this one had coordinates 6, 11? Now you might wonder how calculus is going to do that job. Right? We know how calculus can tell me increasing, decreasing, local max and min, right? That's what we've been doing today. But how does calculus tell me this? And what might surprise you is it's all about the second derivative. Now, this might seem back to front. It might seem, I hope, sensible. But a function will be concave down when its second derivative is negative. And it will be concave up when its second derivative is positive. Does that make sense? And it will have a point of inflection. When the second derivative is 0. Isn't that analogous to what you do for increasing and decreasing, right? Increasing, first derivative is positive. Decreasing, first derivative is negative. Local max and mins happen when the second derivative is 0 or undefined, right? Technically speaking, I've said that. Points of inflection can happen the same way, right? So a point of inflection is a change from a positive to a negative. So that's where they are. It doesn't guarantee that there's going to be one there. So to show you what a point of inflection can look like, that's a point of inflection. Is that a point of inflection? That's definitely a local minimum, but is that a point of inflection? Now remember, a point of inflection is a point on the curve where a concave up changes into a concave down, or vice versa. On this side, isn't the shape concave down? On this side, isn't it still concave down? So that is not a point of inflection. On the other hand, that guy, yes. You see a concave down meeting a concave up. But if it has one, the only place it's going to be is when the second derivative is 0 or the second derivative is undefined. Are we comfortable with that process now? And that's what's going to happen on Tuesday. And the math is going to look almost identical to that guy. Do you know the major difference? After I find the first derivative, I then go and do the second derivative. Because aren't my table of signs going to be on a second derivative, right? When is the second derivative positive? When is the second derivative negative, right? So you kind of have to differentiate twice, but after that, it's very similar to what we've done. And I'm sure I've mentioned it, but somebody might have came in late or forgot. Monday is a holiday. I will see you on Tuesday. Homework and online tests. I've now been given one more day, so they're all going to be due midnight Monday. Okay. Bye-bye. Last name and bye-bye for now.
Thank you.
You're welcome. Bye-bye, guys.
I had a question about one of the homework.
Sure.
So on the mean value theorem, on question 4,
Oh,
I'm just-
hold on. Oops. Let me find your question. And I was just fixing the homework so we don't have questions on concavity. Now, okay, Jason, so let's find 151 in your particular question. Okay, where are you, 151? You can't be far. There you go. Oh, excuse me. There we go. Okay, you've just started. It looks like you've just started this question. So which one was it? Number 2?
4.
Jason, which question were you having issues with?
Question 4.
4. Okay. Okay. Let's show you the question 4. See if we can make sense of their answers. Let me make it a little bit bigger. Okay, so you probably have a curve that looks like that.
Which section is this? Because I'm in
I'm in the wrong
4.2,
place.
the mean value
Oh,
theorem.
sorry. I am in the wrong place. Let's try that again. You have lots of windows to get in and out, unfortunately. So 151, 151, 151. There we go. And mean value theorem. And you should be down the bottom. Oh, it looks like it's the only question you're stuck on. 1, 2, 3, and 4. Oh, the number 4 was not used. You don't use endpoints. It has to be between the start and the finish. So that's all.
Okay. Okay, so just the okay. So just the 4 is wrong.
Yeah.
Okay.
So I'm assuming at 4 the derivative was equal to 0. And that's why you put it in.
Yeah.
Right. Well, Rowe's theorem says the answer is between the intervals. So you don't, even if there is one that works, you don't use it. You only use the ones that are inside the interval. And that's why it's only -4/3.
Well, I'm glad it was something simple.
Yeah, pretty much.
Thank you.
Okay. Alec or Harmon, is there any other questions?
I have a question.
Yes, Alec.
Oh, nope, I guess he doesn't have a question. Number 9
On what section, Harmon?
today, actually.
Oh, today. Okay. Let me get out and get into your version in number 9.
Oh no, from the questions we did today on the notes.
I got you. Oh, my notes.
Yes.
All right, let me find number 9. That means I can forget about that and focus on my notes. Number 9. Now that was question 8. Here we are. Got question 9. And so it was on this side, and I think it finished on that side. Right. What was the bit that wasn't making sense?
Well, actually, what ended up making sense was so I know I more so had a question on the derivative number 9. When you did the derivative, wouldn't we have been able to just, rather than distribute the entire thing, just take out negative 1 x to the -1/3? Just take that, just distribute, or just
What you
like
mean?
hold-
Are you saying distribute or take out? Maybe it might be the words you're using are wrong, but what you're conveying is correct. Right now, when you say take out, that sounds to me like you mean take a common factor. Is that what
yeah,
you're
take out x to the -1/3
right?
as a
Which
common
is what I
factor.
did. Yeah, which is what we did.
But I guess what I'm thinking is like, would you say it's more efficient or less efficient to take it out first?
Well, what?
Because like all the way at the top,
You mean I could take
right
it
at
out
the,
here?
or just or up 2 more, like right before, like basically like right there. Because technically, couldn't you take it out there?
Yeah, you could.
Okay.
I'm not sure what it would look like.
Because that's what I.
Oh, well,
ended up
probably,
doing.
yeah. I don't see anything. Did you get this when you were finished?
Yeah.
Then it's fine.
Okay.
Well, yeah, you could have taken it there. I guess you could have taken it out here, which is what I did. Well, not yet. Here,
Yeah.
which is what I did there. So I just took it a little bit slower. But I mean, as long as you finish the differentiation process, right? As long as you've got to here, then it's okay. I wouldn't do it any earlier than that, because if you haven't differentiated it, there's no benefit.
Yeah.
Because it's going to get changed anyway if you did it earlier.
Yeah, I guess I just did it that early because it looked prettier. Everything just looked nicer when I did that.
And I'm not arguing. I think you're right. It probably does look nicer.